Okay guys, my name is Sunay Tripathi. I'm the CTO and one of the founders here at Pluribus Network. Started about 4 years back. We come from the world of the server side and trying to make this strange thing called switching actually be more in line with the servers in the rack. And that's kind of where things are going. So let me start off, you guys kind of saw what we are doing basically, right? But just to reiterate, 3 key areas that we address, right? One is, how do you make the switch more programmable, more server-like? Because bring the entire tool chain from server world and run it on the switch, right? Because if you look inside a rack, you have 40 servers, you deal with them in one way, and there's a top of the rack switch, which is a weird beast, right? Now the interesting part about this thing is that the top of the rack switch is in a very, very interesting place. Everything goes through it, right? Every server goes through it, everything goes through it, so we can actually make that a very powerful thing. So that's kind of the thesis we started with. So one part of our 1/3 of our effort is, how do you make a switch and bring the entire server ecosystem on the switch, right? So like we said before, we start with a server, bring a switch chip in, either Broadcom or Alta or any merchant silicon that you want, and follow the model of a NIC, right? Similar way, get a driver from these guys, but the rest of the stuff is in the kernel. So let's go through that. The second part that we did is kind of, make it a distributed, because networking is a distributed systems problem, right? If you look at it, dealing with one switch is really hard. Dealing with one rack is really hard because you're half the time tracing cables. So we are trying to make sure that you can pull people out from the world of inside the dungeons of the racks into their desks, where they can actually do software stuff instead of tracing cables all the time. And then the third part that we do is, because it's a platform, we build applications on top of it, right? It's an OS, it's Netvisor. So as we go into Netvisor, again, like I said, please ask questions and we'll go through it. We have been running our own network for 2 years, the stuff that runs in Pluribus networks on our own server switches. So what we are logging into is one of the switch, and we're gonna see what goes on, right? So you log in, you can see it's a root shell, right? I'm logged in as root. You can do something as simple as PSR info. You'll see it's a dual socket machine, multiple cores, multiple threads per whatever. You can run your top in here. You see it's 64 gig memory, and that's where we get people weird, like, what's going on here? Why do you have 64 gig memory? Why are you running top on your switch? So you have to remind them at this point, you are really on a switch, because at any given time you can switch into the switch side by typing CLI, right? You can actually do something as simple as a port show. Every port here is visible to you, right? Now, interestingly enough, we'll see port 9. Why are there so many IP address and MAC addresses on port 9, right? VLANs, VXLAN, all that junk. The interesting part here is that it looks like a server connected to port 9 is running a bunch of virtual machines basically, right? And we see that. So the goal here is that in the server world, two ecosystems that are prevalent when you're doing virtualization, right? One is the VMware ecosystem, where you're running vSphere and whatever to bring up VM. And the other system these days that's coming up is the OpenStack ecosystem, right? So if you look at the OpenStack ecosystem, you got Horizon driving a bunch of your VMs and so on and so forth, right? So the goal is to support both without actually needing too much hooks into the server side or any hooks into the server side. All the information you see is because we are the switch, stuff is going through us. You will see our SDN heritage. So the first step is fabric, right? So in this part of the demo, what we'll go through is the OS itself, the fabric, the CLIs, the basic L2, L3, and how this all works, right? Because remember, the goal is that we need to make sure that when we give something new to people, we don't take anything away, right? There are a lot of people who will give you Linux on a switch, but they take away a whole bunch of stuff, right? In the sense that stuff that was possible before is not possible anymore. So our goal is to make sure that whatever you had before, you always have that full L2, L3, CLI, UI, programmability, and all that stuff. And whatever you need on top is there, right? So if you look at a simple thing, fabric node show, you'll see that this machine is a fabric of 3 nodes. That's how we run. If you look at a tour of our office, we are split into 3 parts, and a rack here, another running our infrastructure, another running our server room. And those are the 3 switches that are part of the fabric: Aquila 12, Aquila 2, and PNDev 3. What software rev they run, what version they run, all of it is visible here. So if you go through port show again, going back, you'll see Aquila 12, port 9, bunch of stuff here. Keep going down, you'll see port 15. Now comes the interesting stuff. You'll see Aquila 12 connected to Aquila 2, right, on port 41, 42, 43, 44. And these are multiple trunks. We need more east-west bandwidth. We actually create trunks and so on and so forth. All this is automatic in our world. Again, it's plug and play. I was talking earlier that we follow Apple style quite a bit. So what ends up happening is you need more bandwidth between east and west. You go in, find 2 empty ports, plug a cable in, walk away. Do not touch anything, don't do anything. If there's any multipath necessary, it will be done automatically. If there's any trunking necessary, it will be done automatically, and you'll get more east-west bandwidth, right? So the goal is that, in your rack pods, you isolate it out, treat it more like a server, right? More like a virtual switch that deals with a bunch of VM. It's a contained environment. But you're using TCP/IP, so there's no proprietary protocols, there's no proprietary algorithms, it's all open stuff, right? You keep going down, you'll start seeing the next switch, which is PNDev 3, the ports on it, what are they doing, right? You can start going down further and you will see Aquila 2, all the ports here. So simple things like you're searching for, where is my VM, where is it sitting, which physical switch, which physical port. You just say port show IP, just picking up a IP address, 10.9.9.24, you'll see Aquila 12, port 15 is where this is, right? Similarly, you want to search for something else, you just type that and you immediately see it's there, right? Now, interesting enough, everything is tab complete. If you notice, I'm typing very little basically. I'm using tab quite a bit, right? I think we are working on technology where I don't have to touch the keyboard. We just think and it'll happen, getting there. But port show, right? So you see, very interestingly enough, again, for all the switches across the fabric, what is happening on the ingress side, what is happening on the egress side is all visible here, right? There's cumulative information, real-time information. We go through history. There's a reason why we run with enough compute and enough, memory and storage, that we actually keep real-time data for a while, as long as possible. And then we have stuff like Fusion IOs on the higher end machines, where we can actually put the data in the log file so we can go back in time, and I'll show you some of that.
So I noticed on the last screen there was a VXLAN tab.
Yes.
You don't use VXLAN internally to the fabric, right?
No, we don't use VXLAN internally.
How do you separate tenants, I guess, between, I might have missed that part, but how do you separate different networks between the fabric?
So we separate different network between the fabric either by VLAN or VXLANs, basically. So to answer your question, that's given, basically.
Okay, I just saw all zeros and I was just curious if that was being used.
Inside our environment, we're not using VXLAN, basically, right? And inside our production fabric, we run one large flat L2 fabric, so you won't see much VLAN also, right? Okay. So, this is...
Does that mean it's completely flow-driven internally?
Yeah, that's
yes, internally this is totally flow-driven. It's all L2 fabric, all flow-driven, and I'll show you.
External flows, if you're port channeled, if you're VLAN or rooted or MPLS or...
Yep.
All comes in, flow mapped across your fabric and exposed back into whatever it is on the other side.
I think you got it. To a certain extent, basically, when we connect to a Cisco's or a Juniper on the outside, we pretend we are full-fledged switch, and we talk all standard protocols, basically, but within ourselves, we just do standard stuff, basically, or TCP/IP based stuff, right? And it's all flow-driven. We pick our paths using flows, basically, and oftentimes, you make a best effort. If things are obvious, VLAN works or just standard switching works, you let that happen and you ride that with flows when necessary, right?
You're not using OpenFlow, obviously.
Good question. Are we using OpenFlow or not? So the way we do it is on the southbound side, we don't use OpenFlow. OpenFlow is too slow for us on southbound side, right? The entire switch and processor is fused together. The entire switch is memory mapped into the kernel, basically, and we are looking at registers and modifying things and whatever, right? Because the decision time for any control packet is literally microsecond. This is one thing we have to be very careful. These days on 10 gig network, a typical connection lasts less than a second, basically, right? You can transfer a gigabyte of data in that time. So what you need to do is really get in very quickly. He wants to talk to he, Is it security allowed? Is it policy-wise allowed? Do we need to do something around that? Is there any SLA in there? So you literally have microsecond to figure out what path to take.
So you're
and
talking
make
about
that.
reactive flow instantiation.
Yes.
So that's generally accepted that that's not a good idea. I'm curious if I mean that's great. If your architecture goes away from OpenFlow, I just want to see like why you guys went a different direction, what your specific.
I think
use case
performance
was.
and scale was the real reason why we went different direction. We see OpenFlow as a good way to come and instantiate long-lived flow, policy-based stuff, right? Things that you're interested in, things that
Okay.
are doing that. So like Stanford, for instance, runs on us. They virtualize part of the network that's given by OpenFlow, and what they're doing is security-based policies, flows that they are interested. They see strange stuff, they get interested in another flow. So dynamic flow creation for a small amount is what we support.
So your
not
protocol is
bound
really optimized for fast flow changes.
Yep, exactly.
Like that.
So rate of flow creation, and when a flow is created, how fast you can do I/O from that flow. Those are the two things
And
we
the
are
flip
working.
side is there's a controller in every switch.
Yes.
Because
So it's not
distributed.
popping. So most people have to pop it out and send it off to some centralized controller
Right.
because they have the controller on every switch, which is clustered.
He got it. That is the key part, right? In a pure OpenFlow environment, if I have to control my learning where my brain is not with me, and I have to send a packet out to someone and someone has to make a decision, that's too slow, right? Time passes very quick. Here we are doing millions of operations per second,
Yeah.
basically, right?
And so having that controller locally doesn't obviate having ODL later.
Yeah.
No,
The
not at all.
ODA can still talk to that
Right.
could
Because that's not policy. That's just your control path is
Yep.
just RAM at that
Yep.
point.
So-
you can still use ODL to instantiate
Yeah.
policy and
So-
just do it
So
your way.
talk
one
about
of the
three
things we did is control stat shift. So if you can see on both switches, right, this is the I/O or the control traffic that's between the switch and the kernel, basically, that's running on that switch. So if you can look at it, basically, right, the number of packets, the number of bytes, both between back and forth is fairly high. Typically what we notice, even in a simple rack with 40 servers, bunch of VMs, right, even just the Mac learning itself is a pretty high bandwidth. We are seeing anywhere between a gig plus of control bandwidth that's in flight because you're dealing with tunnel creations, you're dealing with new VMs coming in, VM migrating, you're dealing with Mac learning because different VMs are trying to talk to different whatever. So all that is done in kernel, and you really need a gig worth of bandwidth and going more in extreme environments constantly back and forth, right? So that means that the pipe between the switch and the kernel needs to be pretty fat, and that's where PCIe comes in, right? We in our bigger machines, we run Sandy Bridge processors on these things, and typically the PCI controller is built into the Sandy Bridge itself going forward. So your response time is also very fast, right? Literally we can take decisions in sub-microsecond latency, right? Versus, you have to allocate a memory, send a packet somewhere, get something back, and so on and so
What
forth.
about a latency in and out of the Trident?
Sorry?
Some vendors have told me that latency, like the I/O to the Trident to program the forwarding plane is
Yeah.
relatively slow. Is that
You got it. So that's 100% part, right? So if you look at what people do, right? I mean, typically these switch vendors to seed the market have given a lot of SDKs and code and whatever, and these are things which have grown over 10 plus years, right? They support multi-chips. They're all single-threaded. They're designed for human configuration, not programmability, right? So one of the things we have done, we don't use the SDKs from the chip vendor. We love their switch chips, we love their SX, we use that, but we don't do anything with their SDKs in general, right? Other than maybe configuring the PHYs and whatever, right? So the kernel itself is fully multi-threaded. At any given time, we have hundreds of threads banging on the switch chip. We are fully coherent in terms of state. We make sure that the locking supports multiple threads and so on and so forth, right?
the key differentiator though, isn't it? Because Cumulus Linux, for example, has a single-threaded driver to the chip because they're using the Broadcom SDK.
Most of the people have that,
Yeah.
basically, right? In our case, this is why it took us 4 years to get to this point, basically, because we started with not using the software from these guys and integrating this as part of the kernel itself, right? So one of the things we tell, there are a bunch of new switch chip vendors coming out in market in next year or so, right? And they're all talking to us, and what we are trying to figure out with these guys is that you need to provide a very shim driver, like a NIC driver, where you contain your register map. There cannot be any memory allocation there. There cannot be a thread creation there. There cannot be a lock there, right? So we are fully all you're doing is no state, no nothing, We want to create a VLAN, you just want to write the right register and return the call, right? Nanosecond operation, you're done. And it's all memory mapped right there, so you should be able to do that very quickly, right? So that way the rest of the control logic and rest of the APIs, because the whole goal is to bring applications into the switch itself, right? So people can write their own orchestration engines, things that can take advantage of this. Security is a big area, right? Because if you look at it, everyone is worried about security in a virtualized environment, and you can't be sitting at the edge anymore. You need to be in the network, basically, right? So what ends up being is you need to see new subnets coming up, new stuff coming up very fast. So the interesting part is going to show you is that, history is very important here, right? This is part of the story. So port stats show, I can see the real-time data. Obviously, we can see congestion on inbound and outbound. What happens most of the time, you get a complaint that, okay, I was slow yesterday I think there was something going on. Were we dropping packet? What was the state of the network yesterday between around 10 p.m., right? So we can go and very quickly say port stat show start time, and we can say yesterday 2014, month was 2, date was 20, maybe around 10 p.m. basically, so 20:00, end time 2014 again. We can do 02/20, time was maybe 20:30 maybe. Actually, I can do the math. 22:30 and maybe fix this as well, right? And you can see now this is the stat coming out from last night from 10 to 10:30 p.m., right? You can see what was the traffic profile at that time. You can see in Pluribus networks that's a low time, not many people working. Typically our world stops around 7:38, people go dinner, hang out, put the kids to bed, and 10:30, 11 is when they're back online, and so on and so forth, right? So this is the data coming out, any congestion, no congestion, you can keep scrolling through it. So one of the things we are paying a lot of attention to is that, visibility and being able to prove was thing working or not, right? So this is something that's applying to both the server side guys, the DevOps guys, and the network side guys on the switching side, right? Because what ends up happening is typically the network guy gets the blame. I've done that. I've been guilty of that from my server world. You go charging on what the hell is wrong with the network, right? Nothing is working, and so on and so forth. And by the time you get on the machine and look at it, obviously everything is working, right? Murphy's law never fails. So there's no proof. What happened really? Source of proof is right here, right? Both guys can look at it, full role-based access control. The server guy can actually look at it and not even go to the network guy and start debugging his own applications, because it might be that the network has no issue, right? So that's the kind of stuff that starts to make sense, right? Again, full L2, L3, so you can configure your VLAN. We were talking about virtualized environments, right? Which ports are active, which ports are configured, and all. So if you look at a typical OpenFlow environment, VMware environment or OpenStack environment, basically, right? You can go multi-rack, you can go plug and play, and so on and so forth, right? So VLANs will open up automatically, ACLs will get configured automatically. L2 table show will actually fabric-wide track what is going on, which MAC, which IP. If the VM migrates, you'll see it there, and we keep history for all these kind of stuff, and so on and so forth.
What about overlapping IP space between?
Oh, totally. If they're VLAN separated or VXLAN separated, you can have totally IP, and we actually manage the IP pools as well. So you can actually one of the things we find out that most of the people struggle with what IP pools, NATed or non-NATed, are there, right? So we manage all that also in our environment. You can actually do that, assign them to virtual networks, and so on and so forth, basically, right? So very simply, switching a little bit more on the programmability side. So IP, let me go L2 table show. You can actually just showing the power of the CLI here itself, that you can sort it based on the hit rate. You can see 10.9973 is the guy which is maximum hit, and so on and so forth, right? You can actually choose to format the argument whatever we want. Maybe I don't want to see the MAC address. I want to see the IP address, VLAN. What else do we want to see? Maybe we want to see the hit and the migrate. That's the only thing we want. So you can just format it to get that data. You can actually even say parsable delimiter. I want it semicolon separated. Type semicolon, and it is all semicolon separated. And the reason is because you can quit out of the CLI anytime. Let me just cut and paste this right here, right? So I'm gonna cut and paste this command right here, quit out of this basically, and I'll just type the same thing here, right? Sorry, I need to escape this. And you can dump this to a file, you can parse this, you can put a script around it. So you can say tish while one, right? You can say CLI command, and all commands support the same thing basically, right? Maybe I just use comma, sleep 5, and whatever, right? And it'll keep dumping the file. So the goal is, if you look at the bigger deployments basically, right, even mid-sized deployment, everyone has their own custom stuff basically, right? They can't use OpenStack directly, right? They need to customize it, they need to work with it, they all have homegrown stuff. Goal is to support that right here, right? CLI is fully scriptable. The interesting part is this is the same thing that our C and Java APIs use. I'm not going to go into that, but I can pull you the code, the sample code that we give out and all that, and our header files and C libraries and Java libraries and REST APIs. So you can write your own code here, try it with the CLI, then script it. Then you need more performance, move to C and Java, right? And whatever your needs are. And you can GDB it right here. So the goal is to support both sides of the environments, right? People who are just scripting, trying to use the system, people who are programming and trying to do more with it, right? So I'm going to stop on this side to give you Fabric, a view of how the fabrics and switch and various VLANs, VXLAN stuff works. And then in the next segment, we are going to go into the vFlow side of the things. This is the SDN side that we were discussing, right? The programmability at the flow level. And then the third part, I'm going to go quickly into the analytics side. It's one of the applications we deliver. So I'm going to stop right here, and then we'll start in a moment.
So real quick, a question came in from Twitter, and it's a valid question. With all this custom, bare metal, you guys building your drivers, not using the Trident SDKs, all that stuff, what happens for Trident 3 when they respin the chip? What happens when the next big vendor comes along and it's a better fit for your next generation hardware?
Very excellent question. So the interesting part is we already support Trident 2 and Alta today basically, right? We actually support Trident Plus as well, right? So the interesting part is that our APIs don't change, they're constant. Our kernel doesn't change, they're constant. It's just the driver changing, a very shim part of the driver that's changing, right? There's no magic, because if Trident 3 comes out, Broadcom has to respin their SDK anyway, basically. Broadcom doesn't have a good sense of how to support application over a period of time and how to take care of application binary interface and so on and so forth. We actually give you a full ABI where you write your applications today on us basically. We will make sure that same OS, same code running on our 1U Trident 2 systems or 2U Alta based systems, or tomorrow Trident 3 or Marvel systems or someone else's system, it will continue to work. The only thing that is going to change is a very small driver basically.
So even across your platform, if you went with Intel's platform and Broadcom's platform, your applications on that are abstracted by your driver. So
absolutely. You can actually write the application on our Alta platform, compile the binary there, put it all together, take that binary on our Trident 2 platform and run it right there.
So it's fully abstracted by you.
Fully abstracted.
Yeah, I don't think it would be unreasonable to expect that your API would never change, because that's, you're not giving us programmatic access to the chip, you're giving us programmatic access to your OS.
So I think he is 110% correct.
Yeah.
Let me explain a little bit. Typically the way you do it, server world, we have done this for a while, right? You have a concept of what is stable versus evolving basically, right? So typically you try not to change the stable APIs, right? So we give things around VLAN, things around port configuration, things around, port stats and all. We have already 2.5 years of history with this. We have multiple customers who have used it in different segments and all. These things are becoming stable for us, right? We'll try not to change it. I mean, having said that, in server world we have changed stable APIs, but we very rarely do that. And we control that in major releases, not in minor releases, right? So same model. New stuff that's coming in, obviously we'll add new capability. API will come in, they'll come into the evolving level basically, and as things stabilize, we'll make them stable.
I just want to comment very briefly. If you expose this level of detail externally,
Yeah.
then that's a very good and rare thing, because a lot of APIs take away some functionality. They don't allow you to get very nitty gritty. They expect you to get into the box. But if you can extract that above, allow me to do that remotely. That's it.
Yeah. I mean, let me try to. I have probably the code open in one of the windows. I don't know how it'll show up on the TriCaster basically, but this is the header file we supply. It's the vFlow structure basically, along with all the functions and whatever, right? And this is starting to become one of our stable API basically, right? The C libraries and Java libraries, we actually give you sample code and stuff like that. So if you go to the event code, this is the Java based code, and there's a C equivalent of that as well, because a lot of time you want to have event notifications and all that kind of stuff. So there's already there. Snooping code we give you. So we give quite a bit of hand holding stuff in terms of how quickly can you build stuff, and so on and so forth, right? So
Very cool.